they and he, and I'm going to try and explain to you why there are 5 shapes of database and why you might use each one. So this came out of a discussion with colleagues. I had a colleague who categorized databases in ways I frankly still don't understand, and I said, but it's obvious, there are 5 shapes. And he said, what? So I think the shapes are relational, columnar, document, key value, and graph. I'm going to give you an example of how you might use these, and at least one open source example of each of these. Note that the examples I chose are not the only ones. Go out and do your own research. So we're going to start with relational for reasons that may become obvious in a moment. So here is a table. It's called books. It has 3 columns. They are called ID, title, and author. Each column has a data type. We've got an integer ID, which we're using to distinguish the rows from each other. And we have 2 string columns. One is the title of a book, and the other is the name of the author. I have not written any books. These books are made up. All books in this, examples in this are false. Don't go looking for books called this book and that book, although I want books called that. So relational databases come from a paper by Edgar Codd back in 1970 called A Relational Model of Data for Large Shared Data Banks. Large here is in the context of the time. We would regard these as relatively small, but this was people trying to do what were at the time large amounts of data. The trouble was that the existing ways of creating databases tended to require your program to know the shape of the database. So if you wanted to alter the data, you had to change your program. And also it was all a bit fiddly. He wanted to create a mathematical approach that was just simple enough and just abstract enough to represent just about anything. And I think he succeeded beyond what would have been his wildest dreams, because relational technology has taken over the world these days. And I have a note here to regard him as the granddaddy of relational databases, and perhaps of databases altogether. This paper is online. In the notes, there's a link to it. In his terminology, what he called a relation, we now call a table. This actually took about 15 years to win. Adoption on mini-computers, faxes and so on, was quite quick, but IBM was very reluctant to abandon their older forms of database. And it wasn't until the mid-1980s that IBM, who were very dominant in the big computing world at the time, adopted relational databases, and that became the dominant technology. Now, our original table, we're all used to thinking of in tables, but if you start to increase what's in your table, data it gets very complicated, and you often end up with a lot of duplication. So what we're doing here is we've got a books table and an authors table. And we are using the author ID, which is in red. We can see that the 2 books in the books table have the same author. We can look at that ID across in the authors table. This has advantages when for instance, we have 2 John Smiths. Well, we can say which one we mean. If we were just having John Smith, the name, in one table, it would all get very confusing. This idea that you can link things in different tables by using shared IDs is fundamental to how relational databases work as well. And if you think about it, I think of these as a bit like Python objects with references to other Python objects. An important concept here is SQL, or SQL, which is a domain-specific language for talking to relational databases. It originates in the 70s, so again, very early on from when the original paper came. The original name was SQL, which was a pun probably on a related language called Quell from Ingress, which it was competing with. It couldn't stick with that name because there was a commercial product with the same name and they would get upset. So it became SQL. But that's why you'll hear people talking about SQL. That pronunciation has been around for a very long time. It was standardized in the 1980s, but the latest version was 2023. So this is a language that's still under active development. Because it's standardized, you'll find that just about every relational database vendor has SQL bindings. They're not always quite the same as each other, but there's a lot of commonality. So to create out those tables, these are the SQL statements we might use. So we're creating a table authors. We're saying as an ID column, which is an integer. We don't want the values to be null. We want them to have values. And we're saying this is the primary key. This is the way we identify our records. And then it's got a name, which is a text, not null. The details may differ between databases. And then we've got our books. Again, we've got an ID, which is an integer, the primary key, it's not null. We've got a title, which mustn't be null. And then we've got an author ID. And this is an int, And here we're saying that this references the ID in the authors table. This means that when we add an ID, an author ID, the database can check that we are using an ID that already exists in the authors table. So this keeps our data tidy. This helps stop us making mistakes. And to find the books written by this notional me author, this Tibs, I can select books.title from books, and I need to join together the author's ID in the authors table with the ID in the books table that match. And say I want those to match when I'm looking this up, but I want the author's name to be Tibs, and that will give me this book and that book back. I should point out I've been failing at writing SQL joins since the 1980s. I always have to go and look up how to do this. So don't be worried if you find SQL difficult. SQL, however, is a really good language to learn because it's a different kind of language than the procedural languages we're all used to, like Python, where you tell the computer, do this, do that, do that. In SQL, what you're doing is find out about this, give me this result, and it's up to the SQL engine then to figure out how to do it for you. So relational databases, they have tables, they have rows, they have columns. We're all quite used to that. We've been doing that with paper and pencil for generations. And of course, we're probably used to spreadsheets as well. So these tend to be a very natural way to think. Schema design, saying how the data is constructed, what the data is like, is up front. When you create your table, you have to say what you want your columns to be. So my first example is Postgres, which is the elephant is a very nice logo for Postgres because it's kind of this big, powerful thing. It's had 35 years of active development, which takes us back to 1990. I wrote that down so I'd remember. It's always a good place to start. It's one of my favorite databases. I have favorite databases. Okay, it's pronounced PostgreSQL, which I find, but you're allowed to call it Postgres because of history, and it derives from going back to the 80s. There's a sequence of databases that lead up to PostgreSQL. It's got rich data types, not just integers, texts, and so on. You can store functions in the database, which means that you can have the database run code, which means that your client doesn't have to do it, the back end can do it. It's very extensible. You can write plugins and so on, but also it's very easy to fork it, do things with it, and then if you're nice, push your extensions back into Postgres. A lot of companies have done that over the decades. It's got excellent documentation. So it's very broad, it talks about everything, but it also goes very deep, which makes me very happy because I often find that documentation talks about what I want and then stops too early. And I recommend it as a good place to start if you need a relational database. My second example, though, is SQLite. Now, the author says he pronounces this SQLite, but he also says he doesn't care how anyone says it. So I tend to say SQLite because that's easier. This is a library, and I love this second quote here: small, fast, reliable. Choose any three. So it's a library, it's built into the Python standard library, imports SQLite 3, and you've got it. You can run it at the command line, and when you start it, it creates you a temporary database. It's everywhere. It's on your phones. So it can legitimately claim to be the database that's got most penetration of the world. It's everywhere. It's single user, which you'd expect, because it's a library. It's slightly odd in some ways, and actually the schema is optional, and how the types work is a bit odd. And the documentation recommends using it as a file format rather than JSON, YAML, or TOML for local storage. In fact, they claim that it's sometimes faster than actually creating a text file. It can be faster than fopen to access. And it can be quite portable. There's the extensions to create zip files that you can post around. So when should we use a relational database? Well, it's almost always a good place to start. The technology's been around a long time and is very mature. So if your data fits, which it probably does, and whatever you need to do, there's probably a relational database that can do it, and it's probably going to be fast enough. But we'll carry on to other sorts. So columnar databases. So this looks like a relational database, except I split the columns apart. I apologize for the name of that first column. For reasons that become evident later, timestamp was too long, so this is just DT. So we've got a timestamp, we've got an ID, we've got a book name, we've got a price, we've got how many books we sold, and we've got a customer ID of who bought that book. Someone weird, 923, bought this book twice at the same time. Maybe they were giving it away. What we've done here is to split the columns up. Very simple idea. So columnar databases are in many ways an optimization of relational databases. They're saying sometimes you don't want to access data as rows, you want to access data as columns. Maybe I've got 100 rows, but I typically use 2 or 3 of the columns. So if I have to go away and retrieve all the rows and then extract just the columns I want, that's both wasteful and slow. Whereas if I know I'm going to do that, if I've got the columns stored in the database, I can just get the columns I need. So storing data as columns can already give you a win there. But because we know the data type of the columns, we can compress that data, giving more efficient data storage, so we take up less space, which also means data is faster to retrieve. So this tends to be good for data that doesn't change a lot, because faffing around with data that's compressed is a pain. So here's a view of that same table, but I've shown where we've compressed repeated values. So the yellow things are things where that data is repeated in the next rows. Because it's a column, you can imagine I'm storing it. You need to get a little bit clever about indexing then to actually figure out where we want to be in the compressed data to retrieve things. But that's known technology. This is stuff we've been doing in computer science for decades. So it's fast at adding new rows, and then the compression will happen in the background over time if there's compression. It's fast at adding new columns, which is interesting. In a relational database, adding a new column means adding it to all the rows. It's a slow operation. It's fast at querying a few columns out of many. It's going to be slow at changing or deleting rows, because you've got to unpick all your columns and then put them back together again. So it suits log data, sensor data, pressure, time, humidity, or tons of information you might be collecting. Time series data in general. And actually, any sort of data where you're going to store it for historical purposes, you're not going to change it, but you want to use it for analytical purposes. So you'll see columnar databases used as data warehouses. And my example here is ClickHouse. Now, this is quite a common model. ClickHouse has an open source version, which is the GitHub repository linked there, and a commercial venture, which will give you enterprise editions that do more stuff. And the commercial thing says it's the fastest and most resource-efficient real-time data warehouse and open source database. ClickHouse is blindingly fast for queries. Nicely, because it's essentially still a relational idea, it's still SQL. So everything you've learned about using SQL still works. It's got extra functions and utilities to make it easy to do columnar stuff, but it's very familiar. And interestingly, because of the way it works, records don't have to have that unique primary key, although having one can help. So here on the left is the SQL to create our book sales thing. This is why DT has to be a short thing, because if I did it a timestamp, it didn't fit in my column. I apologize. Let's see if I can get this to work. Whoops. So this stuff down at the bottom here is because we haven't necessarily got a unique ID, it works with merge trees. I'm not going to go into the details of that at all. On the right-hand side, we've got how we would select the top 10 best sellers. So there's nothing very strange. We're actually summing quantities, which is nice, and we're ordering. This is very standard sort of SQL. No surprises there. So one would use it. We use it when you want to query on columns, not rows, and when you have often when you have lots of columns, and when you tend to have a lot of data, which you don't want to alter. Next, we have document databases. Now, these are very much, think of this as storing JSON. JSON is a document in this context. But our example here, it's got the standard stuff you'd expect. We've got this book by Tibs. It doesn't have an ISBN because it doesn't exist. The publisher is me because, etc. The summary is it's very good. Go read this non-existent book. But chapter content is an array, and each of those, chapter 1, chapter 2, is actually meant to be the entire text of that chapter. So document databases come from handling text bases, where you put in a lot of text and you want to manipulate it or to query it. Documents tend to be JSON, and you have indexes which are a collection of documents. And when you search, you get back the data that matched with a relevance score for how well it matched. So you tend to be handling relatively unstructured data, but you want indexes and you want rich querying, and you're tended to store and query rather than update. And my example here is OpenSearch, which is an open source enterprise-grade search and observability suite. I love that. It's so enterprisey. Brings order to unstructured data at scale, and that's our key factor here. So the technology origins are in document processing, indexing, and searching. It's backed by Apache Lucene, which is a project from 1999, big Java library that handles manipulating large bodies of text, tokenizing, searching, and so on. Queries are written in JSON. Schema design is optional. It can be advisable. If you're storing semantic vectors in OpenSearch, you will need to tell it what the data type is. Sometimes if you're putting JSON in, of course, is it a string or is it an integer? Maybe we disagree over time, and so sometimes you need to tell it. Nice thing about OpenSearch, visualization is built in. This is a query. There's more than one way to query, and there's actually a SQL query interface, which I've not used. I don't know how well it works. So here we've got a simple query where we want to match the author Tibs, but we do not want to match the title that book. And we create an OpenSearch client and send that query to the client. This is, I said, as dashboards. An ex-colleague was using OpenSearch to read in stream of Mastodon messages, put them into OpenSearch, and this is a dashboard showing the data live. So this is showing, we've got on the left, we've got the word frequency, and then on the bottom right, we've got the total count and so on. This means you've got your dashboarding for your data in the tool, which is really nice. So use it when you want fast, scalable full-text search, when you're storing indexable JSON documents, when you don't necessarily want to decide what your data is beforehand, you're exploring, and when you want, for OpenSearch, when you want sophisticated analytics visualization without having to go out into something like Grafana or something. Key values. So here we've got, well, it's a dictionary. It's actually a dictionary of dictionaries. It's a picture of a dictionary. So key value databases tend to be fast, that's their aim. They tend to be relatively simple, it's keys and values. They tend to have sophisticated value data types. And think like a Python dictionary, they're a very nice fit for Python. My example here is Valkey, which is a high-performance key value store. Keys are a binary sequence. Don't make them too many hundreds of megabytes long, because they'll be bad keys. Values can be all the normal things you'd expect, strings and lists, hashes. You can have a one-level dictionary in your value. You can't have dictionaries of dictionaries in your values. Sorted sets are lovely. And some weird things, geospatial indexes, hyperlog logs, which I still don't understand, and Bloom filters if you're getting quite sophisticated. We'll get to streams in a second. It's got its own CLI protocol and its own CLI, which is rather lovely. So to set the value, a value on current greeting, we would use this command. The EX60 at the end says, after 60 seconds, that value should evaporate. We want that value to go away. So we can give a time span for values. LSET is we're setting here the 0th value on book list to this book, that's a list. And HGET, we're getting from our hash, on the hash book this book, we're getting the author value out. It's in memory, but persists to disk. The in-memory means that it's fast, but it also limits you to the size of your memory. Not a problem these days, mostly. And we use it for data storage and retrieval. Caching is very obvious, especially leveraging that ability to have values expire. Strangely, I would normally say never use a database for doing messaging, but it's actually got really good pub/sub messaging, publish and subscribe messaging. So subscribe, unsubscribe, publish. We're using the caching ability there. And it has, if you're used to Kafka, you're used to append logs to streaming, it's got streaming support. So you can add to the stream, you can read off the stream, those are independent. So use it when your data fits the key value ID, typically for caching, although that's not the only use, when you want your data to expire, and for Valkey, pub/sub messaging, message queues, and because of its interesting data types. An ex-colleague was using Valkey to track his cats. They had collars that would say where they were, so he was using the geospatial indexing to figure out where they were. Lastly, we've got graph databases. Now, I have history in this. Back in the 1980s, 1990s, I worked for a company inventing the digital mapping world, basically. And back then, relational databases could not store the data we needed to store. They couldn't store big enough things, and they couldn't do things fast enough. So we ended up writing essentially an object-oriented graph database. No one will have heard it. It's not available anywhere. It's never been, and it didn't take off in the industry for good reasons. Not good reasons technically, good reasons commercially. So here we have this book and that book. This book is written by and published by Tibs. That book is written by John, but published by Tibs. And John is actually a pseudonym for Tibs and Alan. So this is not an XY data graph. This is a knowledge graph. This is a graph of linking things, a directed graph. So graph databases tend to have nodes, relationships, and properties. There's no standardization on naming, so you might hear these as objects, references, and attributes, or nodes, edges, and values. Schemas, depending on your graph database, might be implicit, gradual, or designed up front. So ours, you had to design the schema up front, because we were in a digital mapping phase that was sensible. Quite commonly now, where people are using them for data exploration, your schema grows as you create your data. Nodes will have a type that says what they are. They'll have some properties, and they're linked together by relationships. And relationships are links between the nodes. They can be one-to-one, one-to-many, or many-to-one, depending on how the thing works. And depending on the actual database you're using, they may or may not have properties on the nodes. Now, I have opinions on this. Talk to me afterwards. I'm from the old school, thinks relationships should just be relationships. I'm in the minority. Most people think you should allow relationships to have attributes. My example here is Neo4j. Again, it's got commercial and open source offerings. The world's most loved graph database, their commercial page says, and I suspect that's probably true just because it's probably got the most market penetration, if nothing else. The description on the GitHub repository is rather nice. In Neo4j, nodes have labels to say what they are. You have key value properties, and nodes are indexed. So you're getting some of the benefits of other sorts of database. Relationships have a name. They must have a type, a start node, and an end node. So in this case, relationships are all one-to-one, but you can have more than one of the same relationship to point to different nodes. So you get the best of both worlds. They must have a direction, and they can have properties. So it has its own language for talking to it called Cypher, which is rather nice. So the top one is creating a book object node with the name this book, and it's written by the person whose name is Tibs. And from their own examples, this is finding the Kevin Bacon distance from Kevin Bacon to Meg Ryan using a database of movies. And I love this because it's using shortest path, which is a function they provide, and it's saying I want the shortest path between Kevin Bacon through this star operator says any amount of nodes to Meg Ryan. And it has a visualization tool, which is really important for graph databases, I think. And here we can see the answer. The answer is 2, because we've got Kevin Bacon goes to Tom Hanks through Apollo 13, and then goes to, I can't read that on here, to Meg Ryan, so that's a link of 2. So when do we use graph databases? Well, you're probably going to use them less often than everything else. These were here as oh my goodness, I get to talk about these. When you have a knowledge graph-shaped puzzle, there was a talk on Thursday morning on what network analysis tells us about trades, hierarchies, and the world. Go and watch the video, it's fascinating. And this was oh my goodness, this is a really good example of why you would want to use graphs to do real-world stuff. Neo4j is very good for building structures as you learn them, because the schema can be implicit. You build the schema as you go. You can create node types and relationship types as you go. And obviously, if you're working in this environment, you may not be very knowledgeable about how to do this stuff because it's one of the lesser known types of databases. So the fact there will be a community out there of other people using the same technologies is very useful. There's lots of commonality between these. Obviously, they're all databases. They're all storing data. They all have JSON support in one form or another. I mean, obviously, document databases do. That's really quite exciting. And I have to say, the ClickHouse last year did a really interesting paper on how they're really speeding up JSON analysis in their Columnar database, which scares me because the technology being used is so clever. They've all got some sort of vector embeddings if you wanted to do machine learning. Valkey has a module created relatively recently. I found that out when I was researching for this 2 weeks ago. SQLite has an extension. I don't know how you install it, but it is there. And they're all extensible in one way or another. Thank you. So in summary, we've looked at relational databases, Postgres, which is the granddaddy of relational databases in the open source world, and I would say used for just about anything. SQLite, using your programs locally. Play with it. Discover it when you don't expect to. Use it for configuration. Go and find out people who are making distributed SQLite on a fork. There's a world out there. Read the, it's not strictly open source because you can't contribute. Go and read their statement of their values because they're chiming off Benedictine monasteries. It's very interesting. Columnar, ClickHouse, for analytics, for historical data, for data at scale. Document, for text corpuses, semi-structured data indexing, and again, data at scale. Key value for caching, but also for simple pub, sub, and queues, things you didn't expect to be using databases for. And graph for graph network data, which everyone should play with at least a bit, just to break your mind. This is a page of acknowledgements of all the names I don't own, and neither does the company I work for. I'm not expecting you to read that. I work for a company called Ivan. Our logo is a cuddly crab, and I have some stickers I can give you out afterwards if you want. It's not the Rust crab, we came first. We have your AI-ready open source data platform. We provide managed database and streaming services in the cloud. So we have managed versions of Postgres, ClickHouse, Valkey, and OpenSearch, and free versions of Postgres and Valkey. You can get a free trial of our services using that QR code at the top right, and we're hiring. And the slides were created using Tibs, which is a lovely typesetting language trying to take over from LaTeX as being more accessible. It's kind of weirdly like if you smush Python and Markdown together and then stare at it sideways. And Polylux, which means I generated these QR codes in line. I've been Tibs. If I have time for questions, I welcome them. And otherwise, comment afterwards. I would love someone to come and say, but you forgot the 6th type.
Yes, please. We will have some time for questions. Now we have the microphone standing there. If you can't reach it, please hold your hand up. I'm going to come and give this microphone to you.
Hello, thank you for this talk. Have you ever had doubt of which database to choose and you ended up choosing the wrong one?
Sorry, I didn't hear.
Have you ever had a doubt at the beginning of the project about which database to choose and you ended up choosing the wrong one?
Oh, well, back in the days when we were doing the digital mapping, we did try using relational databases, and we hit the problem that we had hundreds of thousands of coordinate values and we just couldn't do it. And then we hit the value they were just too slow. So we tried and found it didn't work. And that was why we decided that we had to write something of our own, which was a difficult decision. So in that case, yes. Otherwise, yes. I mean, for instance, if you're looking at caching, there's Memcache, there's Valkey, there's Redis, there's other choices out there. Choosing between them can sometimes be how does it affect my CI, how does it affect deployability, what's the license, and so on. So it's not something I've had, apart from the historical example, much problem with. But I think definitely be flexible, be prepared. One of the advantages of if you're looking for a managed solution, check whether it's easy to get data in and out, is the other thing. So it's not only about the database, it's about if someone's running the database for you, make sure that you can get your data in and out when you realize that you've chosen the wrong database or the wrong vendor. So for instance, if you come to Ivan, we're running vanilla Postgres, you can just export the data. We can't stop you doing that, we wouldn't. Because you might decide, oh, actually Postgres was the wrong thing. I should have been using ClickHouse all along, or I should have been using OpenSearch all along. So the ability to get the data out and back in again is important. I think the lesson is the same as programming languages. Make a best guess at first, be prepared to change your mind later.
Thank you.
Thank you for the talk. I have a question. Is there any way, or are there any connectors between different types of databases you can use if you want to multiple database types in a single project? Like you have an ID of a document stored in the Postgres, but the document lies somewhere else? Okay,
so strangely enough, this is the thing that we at Ivan give to. So this is where something like Kafka is your solution as a database, a data backbone. So what you can do is you can have, I've got Postgres, I've got ClickHouse, I'll make a connector that writes between the two, and those exist. But your problem is then you're likely to add a third thing and a fourth thing, and you begin to get this spaghetti network of things that are talking to each other. And your solution there is to say, actually, what I probably want to do is to have a stream of data coming in, and the Postgres reads from that stream, and ClickHouse reads from that stream, and Valkey is probably caching the something and so on. And there, something like Kafka Or if you're lightweight, just practicing it, the streaming queue in Valkey means you've got an event queue. So that you can someone puts things into the event queue at one end, and independently, it's not like a messaging queue where your message queue can fill up. Independently, a consumer can read off the end, and then the consumers can cherry pick what they want. So it's a bit like Ethernet, where you shout on Ethernet, and then people listen to the messages they want. Mm-hmm. And that decouples your both ends, and it also means that your databases can take the data they want and not have to wait on each other, and you don't end up with this tangled mess. Mm-hmm. There are talks of the Ivan website about this, and we do Kafka as our recommended streaming solution.
Thank you.
Yeah. Unfortunately, we will have no time for any further questions, but let us thank Tibs for his amazing presentation, and have a nice day.